Okay, let's get started. I'll remind you that just like all the other times that you take notes in class, that you should set up your page for Cornell Notes. You can see the titles up here on the screen right now if you'll copy that onto your notes paper. And I guess some of you might be watching this and not be in my classroom, so why don't I carefully tell you the objective that you should write in the upper right hand corner. Obviously if you are in the classroom you can just look up and see it. But the objective that you should write down is students calculate, sorry, let me try that again. Students calculate volume of pyramids and cones. Students calculate volume of pyramids and cones. Okay, and just like always, even if you're not in class today or if you're watching this with a substitute, when the video is all over and you've done the problems, you do need to come back and write your 2 study questions and your 2 answers to those questions as part of our Cornell notes. Obviously that gets turned in on the day of the test. All right, and hopefully you'll notice that this lesson builds off of our last lesson. We've already talked quite a bit about volume and how we calculate it by counting up the number of little cubes that we can put inside of some three-dimensional object that has space inside of it that we call volume. So if you're starting to get a feel for what that means, today's lesson on calculating the volume of just some new three-dimensional shapes we haven't talked about yet will kind of fit into what you've already begun to understand. All right, and this lesson will kind of have 2 parts to it. If you are watching it in another classroom or at your house, I'd recommend watching the pyramids part first and then actually pausing the video and going and do those pyramid problems. And then when you're done with those, start the video back up and watch the cones part and then work out the cones part as if you were in class. That's the way we're going to do it in class. Sometimes if you have less to think about at one time, it makes it easier to understand what you want to understand. All right, so let's get started by talking a little bit about pyramids. And just like the other day where we talked about the structure of a prism and how understanding that structure helps you calculate its volume, we're going to do the same thing for pyramids. So let's talk about how you build a pyramid. Obviously all of this goes in your math notebook. So first things first, they start almost exactly the same way that prisms did. In other words, you can build a pyramid out of any polygon you want. It really doesn't matter how many sides it has. You could go with a simple triangle, 3 sides. You could go with a decagon that has 10 sides, doesn't matter. Okay, we are going to start with a rectangle. So if you will draw that rectangle on your paper as well. Now if you're looking at that thing and saying that doesn't look like a rectangle, I'll remind you that since we're drawing these figures three-dimensionally, it's kind of look like we're looking at them from the side, and because we have a different perspective with our eyesight on the figure, that's why it doesn't quite look like a rectangle we would expect to look like. All right, and just like with our prisms, the polygon that you start with, a rectangle in this case, has a name. It is called the same thing it was called with a prism. It's called the base. So every pyramid starts with a base. All right, well, here's where things get different. If we were building a prism, we would make a matching copy of that polygon and move it straight up, but we're not building a prism. So how do you turn this into a pyramid? Well, here's what we do next. We're going to draw all of the vertices of that polygon. It's a rectangle, so it has 4, up to a single point which we call the vertex. Okay, so here is my one single point. If you'll put that one single point on your own math notebook. And all we have to do is take all 4 of these vertices of our rectangle and draw them all up to that one point. So here we go, right like that. You can see we've made one of those connections dotted because, like in all three-dimensional drawings, to try to illustrate that this thing has depth, we dot that one because it's kind of behind the pyramid and we're looking through it, and it helps us with that sensation of depth. All right, I will admit that even I think one of these things is confusing. We kind of call all of these points where the edges connect vertices, or each one is a vertex, And then we name this one at the very top the vertex. I think that's kind of confusing. But that's just the way they do it. The very top of our pyramid is called the vertex, even though all these other ones are actually called vertices too. So I kind of sometimes wish they came up with another name for the top one, but they don't. So we'll just kind of emphasize it as the vertex. All right, so we've got our base down here, the rectangle. We also have some other faces. In fact, you tell me, how many faces would this pyramid have? Well, we got the one rectangle on the bottom and 4 faces going around. That would give us 5 faces. We could call this a pentahedron, but we're going to call it a pyramid. And I'll just point out to you that in all pyramids, not just this one, all of the lateral faces, that is the faces that aren't the base, in a pyramid, they're always triangles, every single time. It doesn't matter if your base is a rectangle like we have, or even if it was a decagon, we would still have like 10 triangles going all the way around. They're always triangles. Maybe you even remember what happened in a prism. The lateral faces were always something too. And hopefully you're remembering that they were always rectangles. But in a pyramid, they're always triangles. All right, here's where things get a little bit different compared to a prism. So the height in a prism is just the distance between the 2 matching bases. Well, pyramids have 2 heights. So let's fill one of these in. One is called the regular height. And the regular height is actually the height of the pyramid. And it goes from the vertex at the very top straight down to the polygon that's the base and forms a 90-degree angle. So this right here would be our regular height. It is actually the height of the pyramid. All right, and the variable we like to use for the height of our pyramid, the regular height, is h. So that shouldn't surprise you. We even use that letter h for the variable that represented the height of our prisms that we probably already studied. All right, but that's only one height. We have one other height when you're talking about pyramids, and it is called the slant height. And instead of being the height of the actual pyramid, it is the height of one of the triangles that's a lateral face. In other words, this height right here, not the height of the pyramid, but like if you took an X-Acto knife and cut out that face, that triangle, that would be the height of that triangle. And we call that slant height. Well, what variable do we like to use for the slant height? Well, we're already using h for height, so we don't use that one, otherwise that would be confusing. And you might say, well, let's just use s for slant, but that would be also kind of confusing because s sometimes gets used for side in a 2-dimensional polygon. So why they decided to do this, I'm not sure, but they used the letter L. Now L even has some problems. L looks kind of like the number 1, so what they do is they write the letter L cursively. So would you write a cursive L on that slant height? So that's the variable we like to use for slant height. All right, so that's all you needed to know about a pyramid. Let's take a look at the formula for calculating the volume of a pyramid. Okay, so here we go. Here comes the volume formula for a pyramid. And I got some good news for you. The volume formula for a pyramid is almost exactly the same as for a prism. Maybe if you're sitting there, you can think of what was the volume formula for a pyramid. The volume formula for a prism that hopefully you learned just a couple of days ago. Well, what did we do? We found the area of the base, whatever area that was. If it was a triangle, we used the area formula for triangle, etc. And then we multiplied that area times the height, which was the distance between the 2 bases. Now in a pyramid, you don't actually get that full area all the way up. If you think about it, and maybe I'll go back. If we found the area of that base and then just, and then just started moving it up, would you get that whole rectangle all the way up to the top? Hopefully you can imagine that as that rectangle rises, because the edges of those triangles kind of get closer and closer to each other, that rectangle would get smaller and smaller as you go up. So you don't really get the full area all the way up. We get what, more or less? Would we get more or less compared to a prism? Well, we would get less. So here is the formula we end up using that exactly calculates the amount of volume inside of a pyramid. We do the same thing. We take the area of the base and we multiply by the regular height, but because we get less all the way up, it actually ends up being exactly 1/3 the amount of volume we would have had it been a prism. So area of the base times height, then you just divide it by 3. Okay? Now, please be careful with this formula. A lot of times we divide by 2, and you can find yourself falling into the trap of just by habit dividing by 2, but please notice when you're doing the volume of a pyramid, you divide by 3, and that's just something you need to keep in mind. Okay, with that formula done, I think we're ready to try a problem. So we are going to find the volume of this solid, and there's the solid right there. I would like you to draw that in your math notebook. Okay, so probably if I were drawing this, I would draw the square that is on the bottom. And then I would draw the point up at the very top, and then I would just simply draw in all of those connectors, and hopefully that would give you a decent looking pyramid. You should also draw in this height, and I guess here's my first question for you. Is that the regular height that we actually want to use for the volume, or is it the slant height? Okay, hopefully you answered that is the regular height that we actually use for working out the volume of the pyramid, so that's kind of some good news. And let's go ahead and get started working on this one. So first things first, what was that formula? Volume equals area of the base. So here is the base right down here. We have to find the area of that base. And then we're going to multiply by the height of the pyramid, which is that distance right there. Okay, so here we go. Let's see if we can figure out. Oh, Mr. Ferkin just screwed up. After you do that, that would be for a prism. What did I forget to do? We have to divide by 3. So after we get those two things in there, we get a lot less volume than in a prism. So we have to divide it all by 3. So maybe let's do the easy part first. I can see my regular height is 21, so I'm just going to fill that in. Okay, so really the big part of this problem is just working out what the area of this base down here. And if you can't tell this already, that base happens to be a square. So we have to find the area for the square, and I guess here's probably the most challenging part of the problem. Are they going to tell us how to work out the area of a square? They are not. They're just going to tell you, you got to get the area of that base. You have to know what formula to use. So what formula do we use to find the area of a square? We're going to use s squared, right? That's the formula we use. So in this case, it's going to be 11 squared. And maybe you don't even need your calculator for this. 11 times another 11 would give us 121. Actually, it would be centimeters squared. That is our area. And what will I do with that area? Well, I got the area of my base. I'm just going to drop it in for the area of the base. So there it is, 121. Now you could grab your calculator and do 121 times 21 and divide it all by 3, but I'm going to divide first. I'm noticing that 3 goes into 21. It would go 7 times. Alright, and now we will simply do 121 times 7. Hopefully you have a calculator with you and can grab it. 121 times 7 equals, and it comes out to be the volume. Oh, I wrote the wrong thing right there. Sorry about that, everybody. This should say volume. The volume ends up equaling 847 centimeters. And how do we measure volume? In cubic units. So 847 centimeters cubed. That would be the answer we would get. Okay, let's try another problem. All right, would you please draw this one in your math notebook? So instead of having a square as the base of this pyramid, it looks like we have a rectangle. Okay, and I'll also point out to you that did they give us the regular height that we really want, or did they give us a slant height that we don't want? Oh, that is a regular height. Okay, and obviously if you're watching this on your own device and I start going too fast, you can just reach over and pause it so that you have more time to draw this. But let's go ahead and start working on this one. So volume formula for a pyramid, what was that? Area of the base times the regular height, but divided all by 3 because we don't get the full area all the way to the vertex. Okay, so let's see if we can work on the area for this rectangle right here. So how do you do the area of a rectangle? Well, that's not going to be s squared. It's not a square. It would be what? Length times width. And in this case, what would we do? We would do 5 times 11. Length times width, and that comes out to be 55 centimeters squared. Alright, so volume equals, we got our area of the base, it's 55. Now we need to multiply by the regular height. What would the regular height be on this one? Well, the regular height from the very top all the way straight down, make a 90-degree angle, that looks like it's 12. But this is a pyramid, so we have to divide it all by 3. Alright, I'm going to notice that 12 and 3 are divisible. You could just let your calculator do the whole thing, but 3 goes into 12, what? 4 times? So if I type out, what would this be? 55 times 4 ends up coming out to be, how much volume? 220 centimeters, not squared, that's area, but volume is in cubic units. Okay, one last problem. Let's take a look at this one right here. Last problem. Alright, and this one is actually the most challenging problem. Okay, so I'll give you a little bit of time to draw this one. Okay, this one's a little bit like the pyramid in the first problem we did, where we have a square as our base. So I would draw that square, and then I would draw the vertex up here at the top and label some of those dimensions. Alright, hopefully you have the routine down. To get the volume of this pyramid, just like on all pyramids, we're going to do what? The area of the base, we'll multiply by the regular height, and then we'll divide it all by 3. So let's get started with the area of the base. Here is my base right down here. That is what? A square. So how do you do the area for a square? Well, just like before, it's going to be side length squared. So in this case, it would be 2 squared. That gives me what? 4 centimeters square of area. Alright, I got the area of the base. So here we go. The area of the base is 4 times my regular height, and then divide it all by 3. So as soon as I have my regular height, I'm good. So let's see, why don't I just fill in that the regular height is 3? Well, why don't I do that? Well, can you see that the regular height is not 3? What is that 3? Can you see that that's the slant height? In other words, that is not what we need. What we really need is from the vertex straight down to right there, and we don't know what that one is. So is there a way to turn that slant height into the regular height? The good news is that there is. So what I'm going to do is draw in from where the regular height hits the base, right there in the middle, over to the bottom of the slant height. And do you notice that that gives us a triangle? In fact, it's not just any triangle, it is a right triangle. So you should draw that in on your own picture. Alright, so what we need is our regular height. If you look at this, the regular height is actually a leg of this right triangle. And we do know the hypotenuse, which is the slant height, is 3. However, that's not enough information to figure this out, but here is the really good news. This regular height comes down and is actually right in the middle of the base. In other words, if this right here is 2 centimeters, and that's right in the middle, can you tell me how far this must be? Well, it must be 1 centimeter. Does that make sense to everyone? Can you always just cut the length of that edge in half? Yes, you can. On all the problems I will give you, you can just cut it in half. And if I know these two sides, can you see that I can solve for this leg, our regular height, by using Pythagorean theorem? So here I go. Leg squared plus this other leg squared must equal my hypotenuse squared. All right, it looks like I should be able to solve for the regular height, so let's do that. Well, h squared plus what is 1 times 1? It's 1. And let's see, 3 squared would be 9. All right, let's get the h squared by itself by subtracting 1 from both sides. So now h squared is equal to what? 9 minus 1 would be 8. And finally, to get the h by itself, I'll take the square root of both sides. So h equals square root 8. Now, square root 8 is not a perfect square, but it looks like we can take a perfect square out of there. So which perfect square is inside of 8? 4, 9, yep, 4 is. 4 times what? 2. Because 4 is perfect, when I take the square root, it comes out as 2. So what is the regular height on this thing? It is 2 square root 2, and that's what I'm going to drop in right there. It is 2 square root 2. All right, let's multiply this all out. Well, can you multiply 4 times 2 square root 2? Yep. You just multiply these together, so we get what? 8 square root 2 all over 3. Can you actually divide by that 3? No, nothing up there is divisible by 3, and it might look a little ugly, but that right there would actually be the volume that I'd expect you to write on the test. 8 square root 2 over 3 centimeters cubed is the volume of this pyramid. All right, up next we're going to talk about cones, but if I were you, I would, and I were like working on this in another classroom, something like that, I would pause the video right now and grab my homework paper and I would start working on it. All right, and I will point out this might not apply to you, but if you're watching this in April 2018 and you're a junior and you're just in another classroom because of our SBAC testing, that all might sound weird to everyone else that this video kind of wasn't designed for, and I'm just showing it another time. But I'll remind you that you do not need to work out problems 12 through 20 on the assignment I gave you in this particular year. If it's not 2018, you should ignore everything I just said. But for those of you who are watching this in 2018 and you're a junior, you don't need to do numbers 12 through 20 on the problems. All right, when you're done with the pyramid problems, you should come back and watch the cone notes and take notes on that. You can stop the video now if you're planning on doing those problems. Okay, welcome back. If you happen to have taken a break to work on those problems, let's talk about cones. This is the last part of the lesson. So let's start by telling you how we build a cone, and hopefully almost immediately you'll see how much it has in common with a pyramid. So if you understood the pyramid part, you should be in really good shape for the cones. So just like before, we're going to start building our cone, but instead of using a polygon, and just like in cylinders, what do you use to start every single cone that ever existed? You always start with a circle. And if you'll remember that makes cylinders extremely predictable and almost easy to work with, is the same thing true of a cone? The answer is yes. So let's start with a circle. And just like before, we're going to look at this thing kind of from the side. So that's why the circle looks the way it does. And just like in a pyramid or back in a cylinder, that circle that you start with has a name. You've probably been noticing it. It gets called what? The base. Seems like everything you start with gets called the base, and that's kind of true. All right, so we got our base. Now if we're building a cylinder, we'd make a copy of that circle, but we're not building a cylinder, we're building a cone. So what we're going to do is draw that whole circle all up to one single point. So let's draw in our one single point. There's our one single point. So we're going to draw everything up to that point. Of course, when you actually draw this, you only draw two segments in, and that kind of symbolizes the whole cone. Okay, and that area that we get, kind of like if you're holding a snow cone or an ice cream cone, like where you actually put your hand, is called lateral area. So we got the area of the base on the bottom, and then we got the lateral area all the way around. Okay, this next part should definitely remind you of the pyramids we did earlier in class. Guess how many heights cones have? They have two heights. Two heights. Okay, there's first the actual height of the cone, and that goes from its very top point, the vertex, straight down to the base at a 90-degree angle. We call that the regular height. Okay, so the regular height goes straight up from the center of the circle all the way up to the vertex. I bet you can tell me which variable we like to use for the regular height. We like to use h, just like in a pyramid. All right, in fact, a little bit later when we do the volume of these cones, that's the volume we want to use, right? The volume's on the inside of the cone, and that's where that regular height is, so obviously that's the one that we want to use. But cones have another height. That's called the slant height. And the slant height goes from the vertex at the very top, but it doesn't go straight down. It goes to the edge of the circle. Just like this. That is the slant height. It's like that distance from that pointy part all the way out to the very edge of the circle. And just like we did with pyramids, we are going to use a cursive L for that slant height whenever we need it. Okay, with those details of a cone done, let's talk about the volume formula that we will use to do our problems. And here's where things get really predictable. Guess what? Is it the same formula that we used for a pyramid? Yes. We're going to find the volume formula. We're going to find the area of the base, multiply by the regular height, and then divide by 3. But here's the catch. In a cone, that base is always the same thing. It's always a circle. So if you know the area formula for a circle, you'll be able to figure out what volume formula we're going to use. Here it is. The volume formula for any cone is to do pi r squared, which very simply is the area of the base, which is a circle, then multiply by the regular height and divide it all by 3. Hopefully you're noticing the connection this has to the pyramids we were doing earlier in class. Volume equals pi r squared times the regular height, all divided by 3. Make sure you get that in your math notebook. Okay, I think we are ready to try a problem. So would you take a moment and please draw this cone in your math notebook? In my opinion, and like I usually point out, I'm no person to be giving opinions on drawings, but out of everything you have to draw in this unit, which I find kind of challenging to draw, I think cones are the easiest. Okay, so let's get started by putting down our volume formula. Volume of a cone is what? Pi times the radius squared times the regular height, but because we don't get the whole circle all the way up to the top, as you rise, that circle gets smaller and smaller and you get less and less volume. We're going to reduce the volume, and we get the exact right amount by dividing by 3. All right, and let's have you notice that when you're doing the volume of a cone like this, really, you just have to plug in 2 lengths and then do the rest of the problem. All right, so what do we get here? How about the radius? What would the radius be? Well, the radius is obviously 5. Okay, and how about the regular height of this thing? That would be 10, so we'll plug that in. Okay, and we'll just remind you that whenever you work this out, you always have to do the exponent first. So let's go ahead and do that exponent. Let's see, 5 squared, 5 times another 5, that would come out to be 25. So what do we get here? 25 times 10 would be what? 250 pi all over 3 centimeters cubed. And 3 happens to not divide evenly into 250 pi, so that's how we would write that. Can I also point out to you that normally we write the pi on the right side of the number? If you wrote it on the front, I'll tell you right now, I would not mark you down for that. That's really not wrong, but just stylistically, we tend to write that pi over on the right, so I'll ask you to try to do that. That's really a good idea. Okay, so just like with cylinders, this is actually our exact volume because we have not rounded off. I would like us to take one more step and work out the approximated volume. And you always work out the exact one. If they ask you for the approximated one, you take the exact one, just type it in on your calculator. So would everyone grab their calculator and let's type that in. So we're going to type what? 250 times shift pi button. I'm even going to hit equals. That gives me 785.398. Okay, but I'm just going to leave that on my calculator, and now I'm going to hit the divided by button, and then 3, and that will divide it all out. You have to be really careful that you remember to divide by that 3. So we'll hit that, and we'll round this off to the nearest tenth. So I got, when I typed it in on the calculator and used the pi button, 261.799. And just like before, we're going to round off on the tenth. So I would look at the 9, and what does the 9 do to the 7? Leave it or move it up? It moves it up. So we would get, what, 261.8 centimeters cubed. Okay, that would be the approximated volume that we have rounded off. It's not exact. I also want to take 1 second and point something out to you, a little kind of good way to check your answers. Do you notice up here we have pi, and then down here we have 3 in this volume formula? Can I point out to you that pi and 3 are almost the same thing? It's almost, not quite, like you could cancel the pi with the 3, because pi is almost 3, and 3 is definitely 3. 3 divided by 3 you could cancel. I'll just point out to you that the pi is just a little bit bigger than 3, but do you notice that the 261.8 and the 250 are really pretty close? Will that happen every time? The answer is yes, because it's kind of like you're multiplying by pi, which is 3, and then dividing by 3. You're going to get almost the same number. It should grow just a little bit. So if you get an answer for your volume that's pretty close to the whatever you had right here when you did the radius squared times the height, you should feel good about your answer. All right, let's try this one. Okay, would you please draw this cone in your math notebook? You'll notice that this cone's kind of pointing down. Does that really change working out the volume? Of course not. Okay, so draw that circle, draw the point down below, fill in those lines, fill in the measurements, and let's see if we can work out this volume. So volume equals, what is that formula? Pi times the radius squared times the regular height, all divided by 3. I'm going to rewrite that formula, but I'm going to leave some spaces for my values. All right, and let's plug some of this stuff in. So the radius, there's the radius right there. That would be 3. And is this the height that we want? Is that the regular height, or is that the slant height that I don't want? Well, that's the regular height, so that comes in at 8. Okay, I've got everything plugged in. I just have to follow the formula. So let's do our exponent first. 3 squared, that would come out to be what, 9. I think right off the bat, I'm going to notice before I multiply, actually 3 goes into 9. So how many 3's go into 9? 3 of them. So what is the volume of this one? Pi times 3 times 8, well 3 times 8 is 24. 24 pi millimeters cubed would be the volume of this cone. That is the exact volume. Let's take it one more step and work it out on our calculator. So here I go. 24 times pi equals, and round this off to the nearest tenth, so 75.39. What would the 9 do to the 3? It would move it up. So we'll call this 75.4 millimeters cubed. This is our approximated volume because I had to round off. It's not exact. Okay, I think we've arrived at one last problem. One last problem. Here is our last problem right here. If you'll go ahead and draw this one in your math notebook. All right, we are going to work out the volume of this cone. So maybe I will start with the volume formula for a cone, which is pi times the radius squared times the regular height, all divided by 3. And I hope you have already noticed that they are telling us that this right here is 8. And what's the big problem with that? Well, to work out the volume, we need the regular height. And what have they given us? They've given us the slant height. So probably the first thing we should do is draw in our regular height right there. There is our regular height. I'm even going to call it H. And hopefully you notice that inside this pyramid, inside this cone, we have a nice right triangle. And we know 2 of its sides, so can't we find that leg that will end up being our regular height by using Pythagorean theorem? Let's go ahead and do that. The regular height squared plus the other leg, the radius, should equal my hypotenuse, the slant height, squared. So let's see, h squared plus what, 25 is equal to 64. I'll subtract 25 from both sides. So now h squared equals, let me borrow, 14 minus 5 is 9, and 5 minus 2 is 3. I'll take the square root of both sides. So my regular height is square root 39. And actually that square root 39 is not a perfect square, and it doesn't even simplify. There's no perfect squares in square root 39. So it might seem a little weird, but this has a height of square root 39. Which, let's see, if I estimate it, is just a little bit more than 6, right? Square root 36 would be 6, but this is square root 39. Maybe if I had to guess, I'd say like 6.2 or something like that, but we're not even going to do that. We're just going to use square root 39 as our regular height. So here we go. Volume equals pi times the radius squared times the regular height, which I just figured out, all divided by 3. All right, who is going in for the radius? The radius of my circle is 5, and the regular height is square root 39. All right, so this looks a little weird, but here we go. What is 5 squared? It is 25. And actually, you really can't multiply or divide anything else. So the final answer for this one comes out to be 25 pi square root 39 all over 3 centimeters cubed. Do you notice, like, since none of that can really be multiplied or divided, you just kind of write it all out? I will point out that the order you write the 25, the pi, and the square root 39 really doesn't matter. If you put those in a different order, I would still give you credit. But that's probably the most common way to put it. The pi right after the number, and then the square root 39 after that. All right, let's see if we can take this one more step. This is the exact volume right there. Let's see if we can do the approximated volume. So here I go. I'm going to do 25 times pi first. When I do that, I get 78.53 blah, blah, blah. And now I'm going to hit times. I'm going to hit my square root button, and I'm going to type in 39. And I hit equals. Now I've got 490 point, a bunch of decimal stuff, and there's just one last thing I need to do. I need to divide all that by 3. So I'm just going to hit the divided by button and hit 3 and hit equals. And there is my final answer. Of course, I need to round it off. It says 163.49. 163.49. And of course, what does the 9 do to the 4? Leave it or move it up? It moves it up. So we'll say 163.5 centimeters cubed is the approximated volume. All right, and we had to do all of that work because they gave us the slant height instead of the regular height, and the formula says you always use the regular height when you're doing the volume of a cone. Okay, that is the whole lesson on finding the volume of pyramids and cones. If you haven't worked out the cone problems yet, now is a good time to do that. And like I mentioned earlier, if this is 2018 when you're watching this and you maybe are in another class because of the SBAC testing and you're a junior, you don't have to do numbers 12 through 20. But if you're anybody else, you do have to do numbers 12 through 20 to get full credit on the assignment. All right, I will see you next time.